We continue the chapter work energy power, and the question we are discussing, that is, this is the NCRT question, and one of the important question example of NCRT. So the second part, we were doing work done by the applied force over the upward journey. When the body is going up, then the work done by the applied force. Applied force is F, and work done equals to force into displacement. So firstly, we find the resultant force F acting upward direction, and mg sine theta and Fk acting in downward direction. So F equals to mg sine theta plus Fk, and Fk equals to mu k into R, and R equals to mg cos theta. Then work done equals to F dot S, and we get the value 18.5 joule. Now the next part we discuss, part number 3 of this question. And this is third part, work done by frictional force over the round trip. Work done by frictional force. Work done by frictional force over the round trip. Work done by the frictional force over the round trip. Round trip means going up and again coming down. So the total work done by the frictional force, and frictional force is the opposite force. So the work done will be negative, and W equals to work done by the frictional force, WF equals to minus Fk. It is the opposite to the applied force, and in a round trip means going up and coming down, so displacement will be L plus L, distance L plus L. So minus Fk into 2L, and the value of Fk is mu k into R. So minus 2L into mu k into R, which is minus 2L mu k, and R is given by mg cos theta. So minus 2L mu k mg cos theta, and put the values. So minus 2 into L is 10, mu k is 0.15, mass is 0.3, 9.8, and cos 30 degree, which is 0.86 or root 3 by 2. When we solve, we get the result minus 7.6 joule. Minus 7.6 joule. So this is the work done by the friction. Work done by the friction, WF, in a round trip, minus 7.6 joule. Minus 7.6 joule, this is the work done by the friction. Now the fourth part we discuss. The fourth and last part of this question is kinetic energy of the body at the end of the trip. The fourth part we have to find kinetic energy of the body at the end of the trip. Kinetic energy when the body is going from top to bottom. This is equals to work done by the net force in moving the body down inclined plane. which is equals to work done by the net force. Work done by the net force moving down the inclined plane. Moving down the inclined plane. So kinetic energy of the body at the end of the trip must be equals to work done by the net force moving down the inclined plane. Now we find the net force acting on the body. So mg sine theta, when the body is going from top to bottom, when the body is going from top to bottom, then force of friction acts in upward direction. When the body is going downward, then force of friction acts in downward direction. Force of friction acts in upward direction when the body is going down. So mg sine theta must be greater than Fk. This is mg sine theta. Mg sine theta must be greater than Fk because body is going down. So work done equals to mg sine theta minus Fk. Fk is the force of friction, and mg sine theta minus Fk is the resultant force by which the body is going down and into displacement. Displacement means L. So mg sine theta minus Fk is again written as mu k into R into L. So mg sine theta minus the value of mu k as it is, and R is written as mg cos theta into L. From these two terms we can take mg as common, so mg and sine theta minus mu k cos theta into L. Now put the value of all these. So mass is 0.3, the value of g is 9.8, sine 30 0.5 minus mu k 0.15, cos 30 degree root 3 by 2, and L is 10. So after solving we get the result 10.90. 10.90. So this is the kinetic energy of the body at the end of the trip, which is equals to work done by the net force moving down the plane. So when the body is going from top to bottom, then mg sine theta acts in downward direction and Fk, force of friction, acts in upward direction. Mg sine theta will be greater than Fk. So mg sine theta minus Fk into L, and Fk is written as mu k into R. Then we get the work done in moving the body down the plane. Now the next topic which we discuss, that is elastic potential energy. The next topic is elastic potential energy. Elastic potential energy, in which we study restoring force and spring constant. Restoring force restoring force and spring constant. This is the initial position of the spring. A mass M is attached to the spring. This is the initial condition. And at this position, x equals to 0. Now the spring is stretched in forward direction. The spring is stretched in forward direction. And in this position, the displacement is x. Here x is equals to 0. Here the displacement is x. A spring is stretched in forward direction. So the external force F acts in forward direction and the restoring force acts in backward direction. F restoring force Fr acts in opposite to the applied force. Now the spring is compressed. This is the third condition. When a spring is compressed, a spring is compressed by distance x. So the external force acts in backward direction and the restoring force acts in forward direction. Restoring force always always opposite to the displacement. Here displacement in forward direction, so the direction of restoring force is opposite to the displacement. Here displacement is in backward direction, so restoring force acts in forward direction. At this distance this is in negative axis, so it would be taken as minus x. This is positive x, plus x. At initial condition, this is called normal condition when x equals to 0. Normal condition when x equals to 0. And external force is represented by F external. F external. And restoring force is simply represented by F. F is the restoring force and F external is the applied force. So when a spring is stretched or compressed from its normal position, when a spring is stretched or compressed from its normal position. When a spring is stretched or compressed from its normal position by a small distance x, by a small distance x, when a spring is compressed, in second condition, the spring is stretched. the spring is stretched, and in third condition, the spring is compressed by a small distance x, then a restoring force is produced in the spring. Then a restoring force, is produced in the spring. Then a restoring force is produced in the spring to bring it to the normal position. Produced in the spring to bring it in the normal position. The first case was the normal position. A mass M is attached to the spring and one end of the spring is fixed to a wall. This is the second condition when the spring is stretched. This is called normal position of the spring. This is the stretched position of the spring. And third position is the compressed position of the spring. Compressed position of the spring. So in the first condition, the spring is in normal condition. Displacement x equals to 0 because no any external force is applied to the mass. This is the second case when the external force applied in the forward direction. Then the restoring force will develop in the spring. When an external force F is applied in the mass M, then a restoring force develops in the spring in backward direction, in opposite direction to the external force, which try to bring the mass to its normal position. And in third position, when the external force is applied inward, then a restoring force is developed. F is the restoring force which develops in the spring. And again, this restoring force tries to bring the mass to its normal position. To its normal position means to the position at x equals to 0. So, when a spring is stretched or compressed, from its normal position by a small distance x, then a restoring force is produced in the spring to bring it in the normal position. And according to Hooke's law, Hooke was scientist. The restoring force according to Hooke's law, the restoring force developed in a spring is proportional to displacement x. The restoring force developed in a spring is proportional to displacement x. Restoring force developed in the spring is proportional to displacement x, and its direction is always opposite to the displacement, and its direction is always opposite to the displacement. So according to Hooke's law, when the restoring force, when an external force is applied to the mass, the restoring force developed in the spring, and the restoring force developed is proportional to the displacement. If the restoring force will be more, the displacement will be more. If the restoring force will be less, the displacement will be less. And the direction of restoring force is always opposite to the displacement. Displacement, in this case, displacement is in forward direction, but restoring force acting in opposite to the displacement. In third case, the displacement in inward direction, restoring force acts in outward direction. So F restoring force developed is directly proportional to minus X. Minus sign shows that restoring force is opposite to the displacement. F is proportional to minus X minus sign shows that restoring force is opposite to the displacement. So F is proportional to minus X and F equals to minus K into X. F equals to minus K into X, where K is called a spring constant. Where K is a constant called a spring constant. F is proportional to minus X. Minus sign shows that restoring force developed is opposite to the displacement. When we remove the proportionality sign, we get F equals to minus Kx, where K is called a spring constant. And if X equals to 1, if the displacement is unity, then F equals to K. Restoring force is equals to a spring constant. When X equals to 1, then restoring force F is equals to a spring constant. Thus, a spring constant is numerically equal to the restoring force. F equals to K means a spring constant is numerically equal to restoring force required to produce restoring force required to produce unit displacement. Unit displacement in the spring. Unit displacement because X equals to 1. When X equals to 1, F equals to K. Means a spring constant K is numerically equal to the restoring force required to produce a unit displacement in the spring. F equals to K. Restoring force is numerically equal to the spring constant. If required force is more, then a spring is said to be more stiff. If the required force or if the restoring force is more, If the restoring force is more, then a spring is said to be more stiff. Then a spring is said to be more stiff. If the restoring force is more, then a spring is said to be more stiff, and if the restoring force is less, then a spring is said to be more soft. Stiff means hard. If the restoring force is less, then a spring is said to be soft. If the restoring force is less, then a spring is said to be soft. So softness or stiffness depends upon the restoring force F. So it means K is a measure of stiffness and K depends on F. K depends on F. So K is the measure of stiffness or softness of string. And the value of K is equals to F by X. A spring constant K equals to F by X. And the dimension of K is, the dimension of force is mass into acceleration mlt raised to the power minus 2 and displacement L. So L and L cancelled, and the dimension of a spring constant is m L naught and t raised to the power minus 2. And the unit of a spring constant, unit of K, the unit of force is Newton, and the unit of displacement is meter. So the unit of K is Newton per meter in SI system or MKS system. And in CGS system, its unit is dial per centimeter. In CGS, the unit of K is, the unit of a spring constant is dial per centimeter, and in SI system or MKS system, the unit of K is Newton per meter. So this is about the restoring force and a spring constant. This was the initial position, normal position, when the displacement x was equals to 0, when the spring is stretched, the external force acting in forward direction, the stretching force acts in forward direction, and the restoring force developed in the spring which acts in the backward direction. When the spring is compressed, the restoring force acts in forward direction and the applied force, external force, acts in backward direction. Here displacement is positive x, here displacement is negative x. And from Hooke's law, F is proportional to minus x. Minus sign shows that restoring force is always opposite to the direction of the displacement. And when we remove the proportionality sign, we get F equals to minus kx, where k is called a spring constant, and for x equals to 1, F equals to k. This is the numerical value, that's why we have ignored the minus sign. So a spring constant is numerically equal to the restoring force required to produce a unit displacement in the spring. And two important things: if the restoring force is more, the spring is more stiff, and if the restoring force is less, then the spring is said to be soft, and K is the measure of stiffness or softness of the spring, and K equals to F by X. Its dimension is m naught L T raised to the power minus 2, and its unit is Newton per meter or dyne per centimeter.